This video is brought to you by ASRock and the Z490 chipset. Yeah, it's Black Friday. Intel stuff is on sale. 10 cores, 10 900K, 10 850K, 10 700K. If you can get a deal, these are the highest end motherboards you can get. The Z490 Aqua, we got one that ASRock sent to us. This motherboard is nuts. It's a built-in monoblock. It can cool the 10 900K with a 360mm radiator, 5.3 gigahertz. Completely insane. RGB, of course. You got that custom monoblock. It's a super high-end Z490 motherboard, although you can also get the affordable Z490 Tai Chi. That's also seeing a price cut this week. There's a Newegg link below. Check that out. The Z490 Tai Chi can basically do everything that you need to do. It's not as high-end as the Aqua, obviously, because you're doing a custom loop if you're doing the Aqua. But if you want to use a more standard AIO or a tower cooler, but you still want a really high-end Z490 system with a 10-core Intel CPU or an 8-core like the 10700K, then definitely check out the Tai Chi and the ASRock Aqua. They're really high-end, exceptional Z490 motherboards. And with that, on with the rest of the video. Hello and welcome, everybody. I've got something really exciting for you today. I've got a CEO. Yes, it's a live one. It's a CEO of LIqid. It's Sumit, and I'm really excited about LIqid's technologies. Probably going to do an infrastructure video on the changes that are happening in cloud and the enterprise and data center because they're diverging. But LIqid, I think, is at the forefront of some really amazing developments in terms of composable infrastructure and some of the stuff that they're doing with PCI Express devices. So, hello and welcome, Sumit.
Thank you so much, Wendell. Thank you for having me today. Very excited to be talking to you and sharing more on the LIqid story. Thanks for having us.
So I'm guessing that probably only about 25 or 33% of my audience has heard of LIqid, but I'm very excited for what direction that your company's headed in and a lot of the products. I've sort of been watching you guys from the sidelines for a couple of years, and it's like, oh, there's some people that get it. But what's the elevator pitch for LIqid for somebody that's not in the know?
Fair enough. I think you're generous to saying your big audience 35% no. So thank you for saying that. But we are a startup. We're a startup that's in the infrastructure space. The technology that we play in is referred to as composable disaggregated infrastructure. And at the end of the day, we've delivered two pieces of technology. Number one, we have delivered a software layer that allows you to orchestrate or manage standard off-the-shelf hardware. And then number two, we built some fabric technology, specifically PCIe fabric technology, that allows you to take this off-the-shelf hardware and dynamically compose servers from pools of disaggregated infrastructure. We refer to this as CDI, and let me give you, I guess, the 5,000-foot level of what composable disaggregated infrastructure means. It's really a new way of building servers inside the data center. Rather than building or defining our server by taking devices and plugging it into the PCIe socket of the motherboard, with disaggregation, what we do is we take pools or trays of hardware, so trays of just SSDs, trays of just GPUs, FPGAs, Optane memory, networking cards. We don't care what the hardware is. We take all of those hardware devices, we connect them into a PCIe fabric. We take all of the servers, we don't care what the server is, a 1U pizza box, a 2U pizza box. We take a little PCIe adapter card and we plug it into the PCIe socket of that server, and we again connect that into the fabric. And then we come in with software and we dynamically compose our machines. Take this 1U pizza box, take 4 of those SSDs from that tray, take 12 of those GPUs from the other tray, and compose or interconnect me a server, a bare metal server, just like we were plugging all of those devices into the sockets of the motherboard, except we get delivered on the other side a bare metal server, a disaggregated bare metal server that is as big or small as we want, except that server is dynamic in the sense of when my server needs another storage device or my server needs another GPU, we don't send somebody with a cart in the data center to power down infrastructure. We reprogram that fabric and we hot add or hot remove those devices from that machine depending on what our user or our application layer is requiring. And what LIqid enables is that dynamic composability of the hardware that's inside your data center. So forgive the long explanation, but from a high level, that is what we do.
No, it hits everything, but it's mind blowing because you literally can, as a programmer, as somebody that works with services like Amazon AWS and Linode and Netlify and several other pieces of infrastructure like that, when I'm designing my solution, my application solution and scalability, I'm basically writing my requirements in a YAML file, and I'm using technologies like Docker or Kubernetes or whatever to spin things up. And that works great for just pure compute resources, but it's like, oh no, I need to define in my configuration, I need this many IOPS. I need access to this kind of GPU hardware acceleration. I need access to, SRIOV network infrastructure because the software overhead of dealing with the network side of it is just too much for my particular application. And that's where those, container orchestration things completely fall apart. But then you guys come along and it's like, yeah, we've got our API, we've got our interface, and everything is a PCI Express interconnect. So you don't have any bottlenecks, really. You don't really have any of the overhead of dealing with a proprietary interface. And so as somebody, building infrastructure, I can just define that in a YAML file, hit a few buttons, and then whatever I need as far as compute in terms of physical hardware is made available to me. And so it's kind of the best of virtualization, but with physical bare metal hardware. And all of my PCI Express packets get where they need to go in terms of, the physical hardware interface. And that's why it's so exciting.
You put so many things out there. I'm trying in my brain to keep track of them because you put so many good nuggets out there. So let me talk first about containers for a second, right? We love the concept of containers. Containers is becoming the preferred method of putting software out into the environment, but that's a software thing. In our world, we have physical containers or hardware containers. Even though I have 50 pieces of hardware, I can redefine that hardware in 500 different configurations. So if I'm going to go run something like a tensor workflow, I probably know the best hardware profile for that application. I want two V100s, I want a Mellanox NIC, I want a Platinum processor, I want NVMe storage. In our world, we can predefine that hardware container, that hardware profile, that hardware template, and then one click, launch the hardware machine, and then the next click, launch the software container that's ideally suited for that hardware platform. So that's one way that we look at our kind of platform, is the ability to containerize hardware, the hardware containers per se, or the templates as we refer to them. So that, I think, is number one. The second thing is you talked about existing orchestration layers like Kubernetes, and that's critical and that's key, right? So we use a lot of Slurm orchestration in our environments. And we take our software and we directly integrate northbound with things like Slurm. So in a normal environment, the Slurm engine would come in and say, hey, you know what, give me 4 servers with 4 GPUs apiece. And we'd go back into the infrastructure and find the best fit and deliver that over. And there may or may not be wasted infrastructure, that's deployed in that environment because I wanted 4, but the best fit I had was 8. And kind of that's how we do it. In a dynamic, composable, disaggregated world, the Slurm orchestrator goes into the LIqid infrastructure and says, give me 4 nodes with 3 GPUs apiece and NVMe storage and this much hardware. We go back into the backend infrastructure at the bare metal, create that exact hardware profile that the orchestration layer requested, deliver that machine back up to the Slurm engine, and we don't waste any infrastructure, and we leave the remainder of the infrastructure to be better utilized by other jobs that are coming in. So that's another thing that I think that you touched on that, we're very, excited about, is the ability to tie in with, existing orchestration layers. And then you talked about virtualization, and I'll say 2 comments kind of there. Number one is, with disaggregation, we are building the physical hypervisor. That at the end of the day is what we are doing. We are doing for physical hardware what VMware is doing for a virtualized environment. But the reality is this thing is not intended to necessarily replace the hypervisor. We think the best of both worlds is HCI plus CDI. Let the hypervisor go down into the infrastructure and say, give me another SSD, I want to slice it and dice it. Give me another GPU, I got a VDI spike. So we're starting to see that happen today, the convergence of hyperconvergence and disaggregation, which is an oxymoron all in itself, but that is where we are headed.
No, that's that I think a few key players have sort of started to notice that is the most sane direction to head in. And even small companies that have relatively limited resources being able to re-provision their hardware on the fly, even just like, we're in a pandemic situation. Oh, we could take some GPU resources from the R&D department and re-provision that for VDI without anybody having to go to the data center. I mean, somebody could do that just immediately because it's software. That's the great thing about the software-defined infrastructure, is that you can make those huge sweeping changes, and it's just a configuration file ultimately.
It's only code, right? So what we're saying is we're seeing this evolution of the data center is what we like to talk about. The three-tiered architectures, the three separate building blocks have given way to hyperconvergence, right? Hyperconvergence is that new buzzword right now as a way to drive efficiency and speed and scale inside the data center. One of the challenges of hyperconvergence is that it's converged. As I scale out, I end up with maybe too much of one thing or not enough of another. So as the evolution continues to happen, hyperconvergence kind of lends its way to a disaggregated composable landscape. So that is how we get the highest resource utilization. That is how we dynamically resize the server for the application as it changes over time. This is where it's not just us, it's not just Gartner, it's even guys like NVIDIA who are talking about the disaggregated composable data center is kind of headed here. So I think we're all kind of starting to see the benefits of why we're doing this, and I think it's important to understand what applications maybe are getting benefit from this. We talked about those VDI and virtualized and vSAN type deployments where we can benefit from deploying on top of disaggregated hardware. Another one is AI-centric workloads. So anything that is GPU accelerator-centric, it benefits from this architecture because, number one, I can scale out. Hey, give me that magic pizza box with 20 GPUs inside of it. No one bends that sheet metal, but doesn't matter. I can compose a server with 20 GPUs. I can share those GPUs. When server A is not using them, go move them to another server. We do a lot in the media and entertainment space. And we have one customer who gives those GPUs to the AI engineers in the daytime. And when those guys go home at night, they reprogram the fabric and they give it to the video rendering machines. Why not use them for video rendering for the next 12 hours when those guys, go home? And we do a lot of these GPU peer-to-peer workloads where it's, allows this RDMA transfer between the GPUs, bypassing things like x86. And we literally see a 10x improvement in application layer performance, leveraging standard PCIe devices, right? So one workload that benefits from this stuff is absolutely the AI stuff. And before I even move on to a second workload, one thing that you mentioned earlier, I think is super important to kind of hone in on is we're at a data center first. This is the first time in the data center that everything is speaking a common language. Yeah. When storage moved to NVMe, it moved to PCIe. When GPUs became relevant in the data center, where do those plug in? PCIe bus. Where do FPGAs go? PCIe bus. Where does your InfiniBand card go? PCIe bus, right? So now we're at this point where everything is speaking a common language, which is PCIe. So at the rack and across adjacent racks, we have a better way to connect these pools of hardware that doesn't require protocol translation, that doesn't require electrical translation, that has the lowest latency out there, by the way, right? People get excited about 1 microsecond InfiniBand. Well, our latency on PCIe Gen 4 is 100 nanoseconds. That's 10x lower latency, right?
Because there's no translation. It's just PCIe.
There's electrons flying back and forth, right? So, it's a data center first in the sense that everything is speaking a common language. And, we get asked, well, why wasn't this done before? Well, the world wasn't ready for this. Everything wasn't PCIe. PCIe Gen 2 didn't support things like hot plug, right? Now we can do hot plug, right?
As somebody who's been troubleshooting things like function level reset on GPUs for the last couple generations to just do my little homegrown VFIO boxes, yes, PCI Express was not ready.
It was not, right? And Wendell, the other thing is, where does it fit and where doesn't it fit, right? And if we think we're going to go run PCIe 200 meters, that's the wrong answer. That's not the game here, right? It's up and down the rack, across a handful of racks, perfect interconnect, right? And the reality is we're going composable beyond PCIe. We're supporting composability on things like Ethernet and InfiniBand. Right now, we can do things like NVMe over Fabric to the same server that I'm doing GPUs over PCIe. Every server should be composable. It may not all be GPUs on PCIe, but hey, storage over Ethernet is a form of composability, and we need to be able to embrace that also.
Well, no, right? I'm a big believer in PCI Express because it's literally going everywhere. I mean, PCI Express at the high end and in terms of interconnects and stuff like that, but also PCI Express at the low end. Most modern SoCs and stuff in your cell phone, like the flash interface, is moving from proprietary buses to just PCI Express. Everything is moving to a PCI Express interface. Literally everything.
It is.
And being able to switch and deal with that and deal with the hot plug and deal with, being able to compose that. I mean, that is the I don't think that I'm the only one that's noticed that, because Liquid's also scored some killer defense contract wins as well.
Yes. No, thank you. Thank you for noticing. And we did. This year we have won over $50 million worth of Department of Defense opportunities to build high performance computing environments that leverage a disaggregated architecture, right? So, we are obviously a small company. The incumbents in this space have been doing it a long time. I think it's notable that we were able to beat some of the big incumbents here, and it's important to understand why, right? How and why did a small company, displace these, juggernauts in the space? It must be something about the technology that's compelling. And I think, what it was three primary things. Number one was composable GPU. The ability to change in these HPC environments the number of GPUs to compute dynamically was very powerful to them. It was a great value proposition. Rather than saying, I'm going to deploy some servers with 2 GPUs, some servers with 4, some servers with 8, and then play this game of workload matching and hope that I get it right, they said, forget that. We want to be able to dynamically take any compute node and make it a GPU compute node and crank it all the way up to 16 GPUs to 1 if that's what we need to do. So we were able to win. Number one was because of this ability to dynamically change GPU count to the server. The second one is going to sound crazy, but we're doing it today, which is composable memory, right? Being able to dynamically change the memory footprint of the server. And the way that we do that is by leveraging Optane. So what we have in our world is we have trays of Optane, and then we connect that Optane over a low latency PCIe 4 fabric to the server. And then we flip the switches in software to be able to treat that Optane as memory. So this is similar to Intel's Apache Pass kind of technology, where we're treating Optane as memory, except we're doing it over PCIe and we're doing it dynamically. So now I can have a tray of memory, carve out 12 terabytes of memory, compose it into a server, and now take a standard server node and turn it into a high memory server node, right?
Yeah.
So
go ahead.
No, and the third one was the dynamic storage capability, right? Let's get away from rotating disk. Let's get to NVMe over Fabric. And it was those three things that really kind of carried it for us, not only once, but across 3 large wins that we got.
Well, I think that a lot of people in the audience that are system administrators right now, or that have some experience in the enterprise, the first time that I heard about being able to do something like that with the Optane memory and deal with dynamic memory, I was like, okay, yeah, there's a lot of bandwidth with PCI Express 4, but there's not really that much bandwidth. But then I actually got to work on a high-end system and actually study how the workload interacts with the rest of the system, and the game has changed. Like, even just completely bog standard NVMe storage is more than enough to overwhelm main memory bandwidth, even in a 2-socket system. So when you talk about having the really insanely huge data sets, it's actually not the bandwidth to the memory that's the problem. It's the fact that the data set is as large as it is to begin with. So, yes, a memory bus is going to have more bandwidth than a PCI Express 4 bus, but when you're talking about data sets that large, from a practical standpoint, that's actually super handy.
Yeah, no, it is. And listen, it's not a panacea. It's not going to solve all problems for all applications, but it is a very, very powerful thing. And on the bandwidth side, remember now a single Gen 4x16 connection, that's 32 gigabytes a second. It's meaningful, right? And we can do more than that into a node if we need to with multiple by 16s and whatnot. But we're getting there. That's one of the advantages is we're able to pool that Optane bandwidth together. And yeah, you're not going to, like you said, you're not going to get memory bandwidth, but you're going to get some
You're going to get
great
enough.
capability.
Yeah, you're going to get enough bandwidth to solve your problem because, at the end of the day, even with an 8-channel system, you're talking about 200 gigabytes per second memory to like socket to memory bandwidth. So, yeah, you throw in enough PCI Express lanes, you can overwhelm that pretty quick.
Our back of the napkin math is telling us about a 1 to 4 on cost. So what 3 terabytes of traditional memory costs, we can deliver, roughly 12 terabytes of composed Optane,
That's really
give
just
give or take.
the
Right?
latency, the low latency is what's exciting about that because if you just manage the data set just a little bit so that you know where it is and you're only just dealing with the latency of getting to where it is, you don't have to scan all of it. It's fine. It's fine. You don't
You
need that
know,
much.
and I'll put some really interesting things out there. Right? When you can get the memory footprint large enough, you can actually do some really interesting math in all memory based applications. Right? Let's just kind of take almost the compute out of it, and forget cores and frequencies and all of that, and just run the math in memory. Right? When the memory footprint becomes big enough, you can start doing some really interesting things. Right?
Yeah, yeah. Well, and PCI Express means that, with those kinds of interconnects, one of the big breakthroughs in networking, it's probably been 10 or 20 years ago almost, was like a zero copy implementation. So you've got a big network job that you're doing, and now sort of, I guess, the modern version of that is like RDMA, where the network card literally is dumping things directly into memory. But in the old days, it was when it dumped it into memory, you just did a lot of pointer arithmetic. You never did a copy. You never copied that out of the buffer and into somewhere else. You just did pointer arithmetic to make it all work. But now with composable infrastructure and a large enough thing, you're doing that kind of thing across a huge infrastructure. So if you do have a huge memory footprint, you don't have to move the data. It can just live where it's at, and you can get at it at high speed.
No, I'm smiling because you touched on the future, right? The future here, right, in these large scale HPC environments, I hate to pick on anyone, is really around bypassing the processor, bypassing main memory copy, and allowing these devices to RDMA directly to each other. We do GPU peer to peer all day today, and we see a 10x improvement in bandwidth and a 90% reduction in latency today when we allow the GPUs to communicate directly to each other bypassing the x86. Well, guess what? The NIC and the GPU already have a direct RDMA path existing today. That's happening today. The NIC and the SSD also have a direct RDMA path that exists today. And lo and behold, NVIDIA invented something called Magnum IO, or GPU direct storage, which is now completing the trilogy per se. It is allowing the GPU and the storage now to communicate with each other. And when you have this finally implemented at mass at the application layer, all of these devices are going to be talking RDMA directly to each other, and the CPU will no longer be kind of that center of the universe, and it'll be more directing the operations rather than doing the operations for a lot of these workloads. So that is where the architectures are headed, and actually PCIe will be a core piece of kind of enabling that at low latency.
Yeah, I think one of the first consumer devices to support that a lot of the people in the audience probably be familiar with were Polaris GPUs. A lot of their, you're going to run multiple graphics cards. They could do their communication directly over the PCIe bus without bothering the CPU. And
Yep.
what you're talking about was incorporated into the PCIe standard because they had the foresight to know that at that point in time. And now you get the marketing people that are like starting to finally understand it. And it's like, this feature's been here for a while, guys. But you have NVIDIA and now AMD. They're like, look what we did on consoles. It's this new thing. And it's like, guys, that's part of the standard. It's been in the Linux kernel for like 10 years now. Come on. Now, granted, it had bugs. There had to be a lot of bugs to be worked out. But it was kind of there.
It's funny. It just takes forever, right? These things, they get invented, and they take a long time to get out there, right? It's just now. I mean, I was one of the original people involved with the NVMe standards document. I can't even tell you how many years ago that was now. 15 years ago, right? We were writing that darn spec, and here we are, fast forward, a decade later from spec completion, and now we're starting to see the world finally adopt these things. So it will take time, but there's no doubt that the performance that's enabled by this will drive the market into that direction. And more importantly, it's the economics, right? If we can now get away from a $10,000 or $9,000 core CPU with 48 cores running X gigahertz to be the center of the world, because now we're doing all RDMA, maybe I can move to a lower end CPU with less horsepower because traffic cop might be kind of the thing I'm more focused on. And I'll just go ahead and lean in and say, with NVIDIA's purchase of ARM, I think we know where they would like to see the world go, right?
I was thinking about, real world specific applications to try to explain how big of a deal this all is to the audience. And I'm thinking even something like Netflix, they've got their pizza box servers and they need to be able to serve movies and stuff like that really easily. The CPUs do a lot of encryption crap like that. The network cards and the bus and everything is so sophisticated now that basically you can just tell the network card, hey, this is where it is on the NVMe. Go read this list of blocks, and when you're done, let me know, and I'll get you the next list of blocks.
That's right.
And then you can do that with a one-core CPU. You don't need much.
You can do it with ARM, right? That's the craziest part about it is you can start now making ARM more relevant, and we're starting to see that also. Believe it or not, we got deployments today that HPC guys are asking for ARM and HPC because we can enable all this RDMA stuff, right? So it's an exciting time out there, right? GPUs are changing everything, right? And they're being adopted everywhere. They are, right? And same thing with FPGAs, right? Lots of interesting new applications, use cases are starting to be accelerated with devices like FPGAs. Right?
Where do you see, like, we've got the moving pieces, but because this is such a fundamental shift in how things are built at scale, I think it's going to enable not just all new markets, but all new business models. And I see like consumer cloud, like AWS, as being one of the first disruptions, because like somebody who builds something, infrastructure wise, having that much more control over the infrastructure that's built for my applications, that's really exciting. But that's just inside my little box. Where do you see it going in terms of like the big picture and the big disruptors in some of those businesses, and especially like cloud businesses?
Absolutely. That's a great question. So we talked about the AI use case. I think we beat that one a little bit good. So that one, you guys understand that. The next one is the HPC use case. I talked about, that a little one. The next one is cloud, and we actually call it dynamic cloud. And so the reality is that this thought and this idea that everything is going 100% public cloud is actually not the way the world is turning out. It's going to end up being a hybrid model. There will be some amount of people that put 100% on public cloud. That will be a minority for sure. There will be some amount of people that maintain 100% on-prem. That will actually end up being a minority also. The reality will be some amount of my infrastructure will be on public cloud. Some amount of my infrastructure I will own and be responsible for. For the infrastructure that I own and I am responsible for, I want cloud-like agility. I want cloud-like flexibility, right? So we think there's going to be a lot of industries that need to build cloud. So take the big hyperscalers aside, there's hundreds of other cloud service and MSP providers out there that provide cloud as a service. They're a great set of customers that can benefit from our technology. There are a lot of financial institutions out there who can't put your bank records on public cloud, but they also want agility on the infrastructure that they own. We think they're a great fit. And we're not saying Bank of America is a customer, but Bank of America went public last year and said they saved $2 billion by not going to Amazon. Nike was out public saying that they got a $60 million a month public cloud problem. So they're sitting around saying, I'm spending $700 million a year on public cloud. What do I do? There's been time and time again of companies, large enterprises who were once on public cloud, and now some amount of their infrastructure is now on-prem. For GPU-centric workloads, for example, we're consistently 70 to 80% less expensive than running on public cloud. So that's the second category. The third category of people is people who are doing clouds, right? Cloud as a service or private cloud, on-prem cloud, some amount of their workload, they're responsible for.
Yeah, that's exactly where I wanted to go with that kind of a discussion, because I see those major cloud providers coming up with what I see is these kind of kludge solutions where it's like, this is your edge compute unit. And really, at the end of the day, where I think, don't let me put words in your mouth, but I think we're kind of beating around the bush. The value add, the way I see it for those cloud providers, is that API and that interface. It's that automation. And it's like, okay, yeah, it's $700 million a year, but we don't have to spool up our own software and infrastructure, and it's all proprietary. They've obviously invested lots of R&D into the software to be able to do it, blah, blah, blah. But what's exciting about LIqid is that if I do want on-premise infrastructure, then I can, negotiate. I can go out. I can get that on-premise infrastructure. But the API that I use to deal with that is exactly the same as an MSP or a cloud provider or something out there on the internet. And Amazon sees the writing on the wall, I think, in some of the other cloud providers, because they're big customers. They're letting them have Amazon regions that are on-premise. And it's like, what? But this is why.
Exactly. You see it, right? You see even the big cloud guys seeing the benefit of having some amount of infrastructure on-prem. And so they're just providing you that solution on-prem to give you an easy on-prem solution. The only reason you go to Amazon is, like you said, the APIs and the ease of use. Give me 4 keystrokes and give me a machine that looks like this. So that ease of use really is what we are providing here at LIqid, except we're saving you a ton of money and giving you higher performance. To make it easy, we do a couple of things. We have a GUI, which is awesome. I encourage everyone to go check it out. It's like almost like an iPad app. You can just move hardware around. It's great. But that GUI is actually built upon a very well documented, rich RESTful API. And then with that API, we give our customers the ability to just script against it using things like Python, or we take that API and we integrate with Slurm. We integrate with Kubernetes. There's Terraform, Ansible, Puppet, Chef, Mass, you name it. There's like a new orchestrator every week. So our job is the easy button for the customer. Let's take our infrastructure, integrate it with the orchestration tools that they're using today, and hit the ground running, right? So that's our focus is.
In my mind, that easy button is worth more than the infrastructure and everything else. That's literally what people are paying for right now, is the easy button. But it's becoming a commodity, and you guys are disrupting it, so it's exciting.
Yeah, thank you. I think there's no doubt that this is the way kind of things are headed. It's just, how long are we going to take to get there? Who are we going to partner with? Who's going to try to go home grow this thing? I think there's a lot of opportunity out there, and I think one of the fun examples I like to use is an MSP we're working with today. And they said their normal onboard process from when they get a customer RFP, RFQ kind of thing to when they deliver back infrastructure to that end customer is 8 weeks. They say, okay, here we go. We're ready to go. By the time they take that inbound in, go get the infrastructure, rack it, stack it, get it stood up, debug it, integrate it into their existing environment, and turn the keys over to that customer so they can begin to use it, it's 8 weeks. And with our disaggregated methodology, they could literally turn that into 8 minutes or less, right? And so for those guys, it's giving them new tools to go off and do things that weren't possible. But I think one of the most exciting areas actually is the fourth kind of bucket we're playing in, which is edge, right? So to me, I think we've been all talking about edge for a long time as this new buzzword. I swear, edge has been the new HPC for a long time, right? Everybody's talking about it. No one actually knows what the hell it is, but it's actually becoming real now, right? So edge is being driven by 5G. The whole speed of light thing is real. We can't make the long distance phone call back to the core data center any longer. There's too much latency in that. So inevitably, infrastructure has to get pushed out close to the cell phone. So it has to get pushed out close to the edge. And what is the edge limited by? The edge is limited by power, by floor space, by cooling. Well, that's what we solve with a disaggregated rack, right? If I can recompose the hardware, at the end, the fundamental benefit that we're providing is hardware utilization. If I can take a static rack that's configured at the point of purchase and getting 20% utilization out of that gear, if I can reconfigure it for different workloads at the edge and squeeze 40% utilization out of that hardware, that's all I care about, because I can shrink power, I can shrink floor space, I can shrink cooling, and by the way, I can take the human out of the equation, right?
Well,
so to me, I think the edge is going to be an awesome use case for software defined.
Just the interconnects. I mean, think about the edge as it exists now, as I'm familiar with it. The interconnects of just translating between all of the different types of compute that you need versus the LIqid solution, which is a PCI Express interface. A whole class of things go away from being a problem. A whole set of heat generators in a relatively confined space go away because it's all PCI Express.
That's right. Right. I think my two favorite edge examples are the forklift example that a customer used for us. Right. They said, "Hey, listen, the long distance phone call doesn't work because if my forklift is being controlled by AI and that decision is being made by a compute element not on site, if that phone call takes too long to the core data center, I could run over somebody."
Yeah.
I think it's got cameras on it. It's navigating through the warehouse. If the latency is not what I need it to be, I could actually hurt someone, right? So that's why, as we push AI out to the edge, the latency related to some of these things is going to be super important, because we're going to be doing real-time inference at the edge. I got a camera, I got a sensor that's pulling in data. It's making a decision. Some of those decisions may be life or death kind of thing, right? So that's one awesome